In earlier video, we already convert the network into AC equivalent circuit. But the BJT transistor is still in graphical symbol. So we need to convert that symbol into AC equivalent circuit. So the first model is a RE transistor model. So in this approach, the important parameter of the equivalent circuit was determined by the actual operating condition. There will be three BJT configuration, which are common base, common emitter, and also common collector. So by these three configuration, we will get three different kind of RE transistor model. Let's reflect the BJT equivalent circuit as in two-port network where the current and impedance are assumed going into the network regardless whether it's an input or an output going into the network. You see the I in going into the network, and then the V in going into the network, the Z in going into the network, and also the output going into the network. Okay, the V out also, Z out also going into the network. So we assume that inside the two-port system is the BJT. Okay, so as we take a look inside the BJT, okay, for the common base configuration, remember that the base is actually connect directly at the ground. Okay, so we call it common base. Then when we see, okay, the terminal here, E is going to, if the IE going to the B, and then the IE also we going to C, the direction of the current for the IE and IC. By examining the input, the transistor's error from terminal E to B, okay, means that the current is supposed to be in that direction. Okay, mean the current will flow from E to B. So we will always refer to this current arrow. Okay, transistor is replaced. As for that, a diode is suitable for its equivalent representation. Mean because of the IE current is flow from E to B, so we said that the diode will be replaced or will be used for the equivalent representation here. Okay, so we change this E to be here, and here is the diode. Okay, and then the transistor is replaced by a single diode between E and B, and then the control current source is between B and C. Okay, this is a current source is replaced at the B and C terminal. Okay, so the direction of the control current source is depend on the current flow from IE to IC. As you can see here, the IE flow to the C terminal, and if we refer to this diagram, the IE will flow to the C. Okay, so that we get this current direction is going up. Okay, and then the current source is IC equal to alpha IE. You should remember this. IC equal to alpha IE. So the important here is IE, the direction of the IE, and then the IC, the direction of the IC, and the current source is IC equal to alpha IE for the common base configuration. Okay, you see the blue color for the I out, for the impedance, for the input impedance, and for the V in, for the V out. These are represent the two-port system network. So we see that the I out is pointing into the system or into the box. However, the IC is in the opposite direction. So I out equal to negative IC. Okay. The IE is pointing into the system. So it is equal to the I in. At the output, the collector current is related to emitter current by equation IC equal to alpha IE. A dependent source is very suitable for its equivalent representations here. This means that collector current IC is controlled by the level of emitter current IE. For AC response, the diode can be replaced with an equivalent AC resistor. Okay, previously we get diode. Okay, we change this one with the diode, and then after that, this diode will be represented with the equivalent AC resistance, or we call it RE. Yeah. So what is RE? Okay. RE is the AC resistance of a diode that are determined as R equal to 26 millivolt over ID. Okay. As for the diode current in this case is IE, so the equivalent AC resistance can be expressed as RE equal to 26 millivolt over IE. So we're going to use this formula for the RE. Every time you see RE, it means that this formula 26 millivolt divided by IE, and it will represent the resistance here. So we no longer use the diode symbol in the RE model for the BJT. Notice the capital letter IE is for DC level. It means that apply DC analysis to determine this value. Okay, even though it is the AC small signal analysis, everything is in AC circuit and the RE model, but there is some values are calculated from the DC analysis. So this is the value that we get or we obtain from the DC analysis. So IE, you see the capital letter E, it means it's from the DC level. This is a complete RE equivalent model that include the input part and the output part. Okay, we have RE with the resistor here, and then the current source IC that represent the IC equal to alpha IE. So at the input now, we get the equation that we derive from this circuit. Okay, first one is the V in. Take a look here. V in is equal VEB, okay, or IE multiply with RE. This is the first equation, and then we know that IE is equal with I in. Okay, it has the same direction. So we get the input impedance, which is Z in, is equal to V in divided by I in, equal to IE RE over IE. So finally we get the Z in is equal to RE. So as we can see directly in this figure, the Z in is the RE. Now for the Z out, it will be determined by the transistor's output characteristic. Okay, you still remember this one? Characteristic of the common base configuration, which the curve is, we can see the curve here, and then this is very flat. Okay, this is very flat, and then notice that the slope remain the same for any input current. Okay, the slope is remain the same. Okay, and the slope is very close to a perfect horizontal. Okay, really flat here. So this means the resistance is infinity. Okay, so we take a look at this circuit, equivalent circuit. Okay, we say that the output impedance for this RE model is infinity. Okay, so there is no resistance here because we say that it like an open circuit.